Hello everybody, my name is Lian Pan. I'm a Senior Manager of Marketing at GenScript, leading protein and antibody services. Thank you all for attending this webinar on identifying the optimal purification strategies for your recombinant protein production. To ensure the sound quality, all of you are muted to minimize the background noise. If you have any questions during my talk, please send your questions through the chat box at the right lower corner of the screen. I will address your questions altogether at the end. Back to June this year, I gave a webinar titled as Protein Expression and Purification, Challenges and Solutions, which is a general overview of recombinant protein production. After the webinar, I received several requests on whether GenScript could offer a more protein purification-focused webinar in future. This is how this webinar was coming up. In today's webinar, we will first review the general process of recombinant protein production. Then, we will go over how to optimize protein expression, as this is the prerequisite step for protein purification. With multiple protein purification methods available, how to work out the optimal purification strategy according to your specific recombinant protein will be discussed in Section 3. Protein tag is one of the mostly used strategies for protein purification. In this section, we will go through the commonly used protein tags and their usage in recombinant protein production. We will also go over endotoxin removal, as more and more recombinant proteins are used for therapeutic purpose, in which endotoxin level needs to be tightly controlled. At the end of my talk, I will go through our most popular protein services and how GenScript stands out from our competitors. For recombinant protein production, the start point would be the name of the protein. You first need to decide whether to express the whole protein or a fragment of the protein, and how you're going to obtain the DNA, by traditional PCR or gene synthesis. Nowadays, more and more people go with gene synthesis, as the codon optimization can be integrated in gene synthesis step to eliminate codon bias in the process of translation, thus increase protein expression. Once DNA template is obtained, it needs to be cloned into an expression vector and then expressed in a chosen system, where DNA construct is to be transcribed into messenger RNA and mRNA is translated to protein. After your desired protein is expressed in the chosen system, protein purification needs to be followed, which is the focus of today's talk. After protein is purified from host cells, protein characterization will be carried out to make sure that the purified protein is your desired one. A critical step in protein production is to choose the appropriate expression system. Let's first take a look at the available recombinant expression systems. Traditionally, recombinant protein have been expressed in bacteria, insect, yeast, and mammalian systems. In recent years, recombinant proteins can also be made in vitro using cell-free translation system. However, this in vitro system is costly and not suitable for scale-up protein production. Most of the times, researchers choose among those 4 in vivo expression systems and use the cell-free system at the last resort. When choosing an expression system, please keep those factors in mind. First is the protein property. What's the molecular weight of the protein? The number of disulfide bonds, whether your protein is subject to post-translational modifications, and whether you need a homogeneous protein expression. Secondly, you need to consider the intended applications of the purified protein. Is it for structural biology studies, or functional assays, or used for therapeutic purpose, or used as antigen for antibody production, or for protein-protein interaction studies? Protein property and its intended applications are equally important when choosing an expression system. As every project comes with a budget, you also need to consider the yield of the protein in the chosen expression system and also the associated cost. Your final decision on the expression system should weigh in all these factors. No matter which expression system you finally choose, at GenScript, we have all the expression systems available, and each is equipped with our proprietary technologies and specific guarantees to ensure the quality and quantity of the purified proteins. I want to point out that all these listed services here are starting from gene synthesis with free codon optimization, and the price includes the gene synthesis fee. In contrast, the price listed by most of our competitors doesn't include the gene synthesis fee, which typically costs 35 cents per BP. For a 2 kb gene, it's easily to add up $700. With our packages, you just need to provide us the sequence of the protein. We take care of the rest and deliver you the purified protein at the specified purity and amount in each package. As our success rate of protein production is so high that we are able to offer the guaranteed packages, which means that if we fail to deliver the protein at the specified purity or amount, it will be no charge to you, so you are risk-free. What makes it better is that we recently started a price match promotion for BacPower, the bacteria expression guaranteed packages. We do not want to lose your business just because of the price. We are confident with the quality of our services and willing to match competitor prices to let you experience our superior quality. In the circumstances that you need protein urgently to meet deadlines, we also have fast gene-to-protein services that deliver you the purified protein in just 4 weeks guaranteed. For insect power, our insect expression system, and manpower, our mammalian expression system, the guaranteed amount of protein, delivery time, and price are listed in the table here. For East High packages, they are totally customizable and the price varies based on individual project. To know how much exactly your project would cost, you can contact our PhD level technical account managers for a free quote. Sometimes it may be hard to decide which system to use, as you may not know which system works the best for your protein. Not a problem. We offer a service called Potential, which is a protein expression evaluation and optimization service that can help you to practically decide which expression system is the best for your protein expression. If you already choose your expression system, the Potential Standard service can help you to evaluate whether your target protein actually expresses in your chosen system before you scale up protein production to avoid waste on your time and valuable resources. With Potential, if your construct shows decent expression, you can just add only $600 for 1 liter expression and purification, which would be the most cost-saving and time-efficient way for your target protein expression. In cases that your target protein didn't express the way as you desired, Potential Silver and Gold packages can help to optimize the expression conditions that give you the most robust soluble expression of your target protein. It is a proven, efficient, and cost-effective way when challenges arise in your protein production. Here, I would like to share with you a protein expression optimization case we did at GenScript. A customer had challenges on expressing a 28 kD protein in large scale. The yield was low, only 1 mg per liter culture, and the protein can only be purified from the soluble part. The customer needs large amount of purified protein. Therefore, the 1000 liter scale fermentation and purification is needed. With the yield of 1 mg per liter, even with 1000 liter fermentation, it only produces 1 gram protein, far from his desired amount. And it would be too costly if further increasing the culture volume. Therefore, the expression needs to be optimized so that the production efficiency can be improved. Here is the list of parameters we optimized for the customer. The parameters included in the potential gold package. And we also optimized the purification conditions to increase the protein recovery rate. Here is the result. By optimizing T7 promoter and the induction conditions such as temperature, inducer concentration, and the induction time, the production efficiency is doubled from 1 mg to 2 mg per liter. By further optimizing full A promoter and the induction conditions, the yield increased to 5 mg per liter. By continue optimizing growth conditions such as media components, pH, the yield increased to 6 mg per liter. And we also did succeeding density optimization, which increased the yield to 12 mg per liter, 12-folds of the original production efficiency. This case gives you a glimpse of our expertise on protein expression optimization. Whenever you encounter challenges in your protein production, don't struggle it yourself. Leave them to our protein experts. It will not only release your stress, but also save you time and money totally. Once the protein is expressed successfully in your chosen system, it comes to protein purification. Almost unavoidably, every protein purification step results in some degree of protein loss. To obtain sufficient amount of pure protein, it's critical to apply the optimal protein purification strategy specific to your recombinant protein, with which the highest level of purification is achieved in the fewest step. Unfortunately, each protein is different, and there is no one applied to all strategy. In order to work out the optimal protein purification strategy for your specific protein, you need to consider the following parameters. First to consider is your protein characteristics, such as sequence, molecular weight, pI, solubility, etc. For bacteria expression, sometimes protein expressed as inclusion bodies, which requires protein refolding. Even for soluble expression, there are multiple protein purification methods available. How to choose the best one for your target protein purification? First, you need to consider whether your protein has a specific ligand. If not, you may consider adding tags to your protein. Also, there are some proteins that are easy to degrade. How should you handle those proteins during purification? What if the protein concentration is too low? How to remove endotoxin in the sample so that the protein can be used for some in vivo studies? With all those questions in mind, let's go through each parameter one by one with some case studies. When protein expressed as inclusion bodies, protein refolding becomes necessary. First, what's an inclusion body? when E. coli is transformed to manufacture large amount of recombinant protein, the protein sometimes forms dense aggregates of insoluble misfolded proteins known as inclusion bodies. Inclusion body is not necessarily a negative factor. The benefit from a production aspect of inclusion bodies is that they allow high protein concentrations, protect sensitive proteins from proteolytic degradation, and protect the cells from any toxic proteins. However, the big challenge is to solubilize and refold the protein into its correct active form. Although all the information necessary for folding the peptide chain into its native structure is contained in the primary amino acid sequence of the peptide, the challenge is that there are vastly too many different possible conformations for a protein to fold by a random search. Consider just for the peptide backbone, there are 3 conformations per amino acids in the unfolded state. It would be impossible to do the correct folding based on a random search. The good news is that a new view of protein folding suggested that there is no single route, but a large ensemble of structures follow a many-dimensional funnel to its native structure. Therefore, practically, we need to find conditions that facilitate this process of protein folding to its native structure. The most challenging part for protein refolding is that refolding conditions must be optimized for each individual protein. There is no standard rule, and the key is the selection of the optimal refolding buffer. When you make refolding buffers, you need to take considerations of these important variables that contribute to the correct protein refolding, including buffer type, pH, ionic strength, additives that are often in combination, such as glycerol, redox reagents, saccharides, amino acids, metal ion, detergents, and chaperones. At GenScript, our in-house scientists developed our proprietary protein refolding technology called FoldArt. It first analyzed the biochemical and biophysical properties of the target protein and then select particular refolding strategy based on protein sequence and its structural properties. Then, solutions for the inclusion bodies will be diluted to 20 different refolding buffers to determine which parameters affect the refolding results. And an optimized refolding buffer will be selected for further refolding assay. Regarding the denaturant removal, 5 different techniques: dilution, dialysis, difiltration, gel filtration, and chromatography will be employed to remove the denaturant. Refolding result will be validated by SDS page, HPLC, and or functional assays. With our FoldArt protein refolding technology, over 95% of the inclusion bodies can be solubilized and refolded. Here is an example of protein refolding we did at GenScript with human interleukin-5. In fact, we routinely do protein refolding when protein expressed as inclusion bodies. The active form of protein interleukin-5 is a disulfide bond-linked homodimer. At the SDS page gel showed here, the first lane is the unfolded protein. Condition 1 to 5 is using different refolding buffer. As you can see, condition 4 gives the most abundant refolded protein at the right size. After refolding, human interleukin-5 was further purified by ion exchange separation IEC, and you can see that the final product showed a very clean protein dimer band on the gel. If you ever need protein refolding services, I encourage you to use GenScript Fold Out service. Don't try those tedious refolding optimization processes yourself. It's just not worth it. Leave it to our experts. Let's quickly go through some basics of protein purification. There are a variety of protein purification methods, including affinity columns such as GST, Nico, Protein A, Protein G, Protein L resins column, etc., and also ion exchange IEC, size exclusion SEC, and hydrophobic interaction chromatography HIC. For big protein, double tag strategy can be applied for purification. The bottom pictures showed a few routinely used instruments at GenScript for protein purification. With a variety of protein purification methods available, how to choose the one that works the best for your protein? As I said earlier, every protein is different and there is no one applied to all strategy, but practically for proteins with special ligands such as antibodies and their fragments, Protein A, Protein G, or Protein L columns can be used. For other proteins, furan tag is a commonly used approach. For small tags such as his tag, Nico, NTA column can be used for affinity purification. For big tags such as GST, glutathione-coated agrospecies can be used. We will get to more details later in the protein tag section next. For tag-free proteins, they can be produced in two ways. One is to express it as tagged protein and then cut the tag off during the purification step. Under certain circumstances, you may prefer no tag expression. This way, tag-free protein has to be precipitated out first by sulfate based on protein molecular weight and pI. Tag-free protein can be separated by SEC or IEC. If tag-free protein has a particular binding domain, such as positive charge domains, heparin column can be used to separate the protein out. HIC is usually the last resort for protein purification. There is a case study on full-length recombinant monoclonal antibody production. Fractions were collected and buffer exchanged into PBS, then analyzed by SDS page, Western blot, and HPLC as shown on the upper right corner here. Our quality stands are purity over 95% by SDS page and HPLC. Even up to 99% purity can be reached. Aggregation less than 5%, endotoxin level 0.05 to 1 EU per mg. Concentration is usually at 20 mg per ml. Host cell protein should be lower than 100 ppm, and host cell DNA should be lower than 100 pg per dosage. With this order, our production team first did a 1 gram pilot transient production to test out the expression level, then developed the industrial grade cell line, followed by 100-liter scale-up production, and obtained close to 50 gram purified antibody. This is a case for Prone-to-Degrade protein. This type of protein didn't present challenge until after you obtain the purified protein. This is an example with a customer in the field of diagnostics. This protein was successfully expressed in 293 T cells. The problem was first identified after we delivered the protein to the customer. The protein concentration customer measured is inconsistent with what we measured before delivery. After we received the feedback from the customer, we immediately started the troubleshooting process. Our production team double-checked almost every step, including transfection methods, cell lysis, and purification steps. As shown on the right upper corner, the Western blot showed certain level of degradation with the protein. The top band is the non-degraded protein with the correct molecular weight. The two lower bands are proteins at a different level of degradation. The first line is the protein with the DNase treatment, and the second line is the protein without DNase treatment, indicating that DNase is only partially responsible for the protein degradation, and the protein itself is prone to degrade. Therefore, besides removing DNase and adding protease inhibitors to every step in the production process, we did further optimize on buffer components, added protein stabilizers such as glycerol and sucrose, lyophilized protein immediately after purification. We also test the storage temperature and found that the protein is more stable at -20 than 4 degrees. The bottom western blot showed the intact protein after the process of optimization. This customer was very happy with the final result. Protein concentration is near the end of protein purification process. I received a few inquiries from customers who lost their proteins in the concentration step. Surely, you don't want this happening as you are almost there to obtain your purified protein. Ultrafiltration is a commonly used approach for protein concentration, in which it can be further categorized into cross-flow filtration and dead-end filtrations. For large volume, you'd better go with cross-flow filtration. You can use either plate and frame module or hollow fiber module. Both allow high work pressure and are easy to clean and replace membranes. If you work with small volume, the dead-end filtration is the convenient way. It can process 15 ml samples in as little as 10 minutes. The recovery rate is high too, typically over 90% with relatively low cost. Here is a case study using slice cassette methods. The membrane molecular weight cutoff is 30 kD and the membrane area is 0.1 square meters. The molecular weight cutoff should be determined by target protein molecular weight. And the target protein S and Q here are around 80 to 90 kD. 30 kD cutoff is pretty safe. The bigger the membrane area is, the faster the filtration is. Line 1 and 2 are protein S before and after concentration. Line 3 and 4 are protein Q before and after concentration. Both were concentrated 20-fold with over 97% recovery. Protein tags are probably the most used strategies in protein production. In this section, we will discuss those commonly used protein tags in protein expression and purification. When using protein tags, you need to consider your target protein characteristics, including protein sequence, PI, molecular weight, and even furin protein concentration. What type of tag to use, whether a protease cleavage site needs to be added, whether a tag-free protein is desired for final delivery. On the protease side, you need to consider the protease activity and its reaction condition, and whether the target protein will be affected by those conditions. Affinity chromatography is the most commonly used protein purification method, especially for tagged protein. The commonly used affinity tags include polyhase, usually 6-hase, GST, MBP, flag, and sumo tag. Each tag has its corresponding matrices and elution conditions. For example, the matrices for his tag protein would be nickel resins, and the elution buffer would be 10 to 250 millimole imidazole or low pH. And the GST tagged protein can be purified through glutathione agarose base and eluted with reduced glutathione condition. Purification can be carried by either columns or batches as illustrated here on the right. If you would like protein without tag, the tags can be digested off by site-specific protease during the purification step, given that a restriction enzyme digestion site was incorporated when making the protein expression construct. Here is a table for commonly used protein tags. You can check out its size, corresponding purification method, and purpose in this table. His tag is the mostly commonly used one due to its small size and unlikely to interfere with target protein function. Flag tag is very specific but costs a little bit more than his tag. For insect and mammalian expression, using flag tag yield much pure protein compared to using his tag. Both his and flag tags are small tags. Tags like MBP, GST, NuSA are big tags, and they are served with different purposes such as increasing solubility, facilitating proper folding, periplasma expression, etc. For tagged protein purification, they go through a routine workflow as illustrated here. First, you need to equilibrate the purification column. Then you add a sample to the column and wash away impurities in the samples and unbonded proteins. Then you elute the bonded target protein. The workflow is very simple. This is an example of one-step his tag protein purification using nickel resins. As you can see from the image, target protein was mainly expressed as inclusion bodies as shown in line 1 and also expressed soluble as shown in line 2. In this case, protein was purified from the soluble part only. Line 4 is the wash with 50 millimole imidazole, and line 5 is the elute with 500 millimole imidazole, and the protein purity is over 95%. This is a case with one-step MBP-Amylose purification. In this case, the protein was expressed mainly in the soluble part as shown in line 2. Line 3 is the flow-through. Line 4 to 6 are elutes with amylose gradient, and each elute has a high purity protein. Line 7 is the resin after elution. If you need tag-free protein, you can either express the tag-free protein directly or express it as tagged protein and then cut off the tag during the purification step. For the latter, when creating the expression construct, you need to insert a protease recognition sequence between the target protein and the tag. This slide listed the commonly used proteases with their recognition sequence, amino acid residues left after digestion, temperature range, pH range, and their molecular weight. This showed a case study on TRX tag removal by TEV protease. The image showing is the SDS page result. The digestion was done at 4 degrees overnight. Len 1 is the furin protein. Len 2 to 4 are tag proteins digested with increasing amount of TEV protease. The top band is the furin protein, the second one is the tag-free protein, and the band in the middle is the TEV protease, and the last at the bottom is the TRX his tag. Certain applications, such as in vivo studies and therapeutic proteins, require proteins with endotoxin level well controlled under a certain limit. In this section, we will go through endotoxin removal together. Endotoxin is one type of the impurities present in the protein samples. Endotoxins, also known as LPS, are large molecules found in the outer membrane of gram-negative bacteria, which elicit strong immune responses in animals. To measure endotoxin levels in the protein sample, either gel clot method or chromogenic method can be used. Both methods are using known concentration of endotoxin to set up the standards and then measure either the cloudiness or color to determine the endotoxin levels in the samples. To keep the endotoxin level under the required limit in the sample, there are three routinely used methods to remove endotoxin. One is affinity-based polymyxin B (PMB) method, such as GenScript toxin eraser, a modified PMB-based affinity matrix that allows highly efficient endotoxin removal down to 0.1 EU per ml. The other two endotoxin removal methods are size exclusion (SEC) and ion exchange (IEC). The endotoxin molecular weight is typically around 10 kD. As the target protein is usually much bigger than that, endotoxin can be removed by size exclusion (SEC) method. When the pH of the solution is higher than 2, the charge of endotoxin is negative. Therefore, endotoxin and the protein can be separated using ion exchange column as well. The table here showed 3 cases of our endotoxin removal services we did for the customers whose sample all had very high endotoxin levels. Each case was using 3 ml resins on 15 ml samples, and we reduced the endotoxin levels up to 2 million-fold, with the final endotoxin levels all below 0.1 EU per microgram. If it's required, we could reduce further on the endotoxin level to less than 0.01 EU per microgram. In fact, at GenScript, we offer endotoxin removal services in 3 tiers: endotoxin levels less than 1 EU per microgram, less than 0.1 EU per microgram, and less than 0.01 EU per microgram. You can choose either one based on your application need. We have gone through some technical aspects of recombinant protein production, focusing on protein purification. In the last section of my talk, I will go through our most popular protein services and how GenScript stands out from our competitors. The first one is that we are equipped with our core in-house technologies for expression optimization and increased protein production efficiency, which enable us to deliver you high-quality protein at low cost. For all our protein expression projects, we can utilize our optimum gene technology to do the codon optimization. We optimize the gene expression from the very beginning, the sequence. In addition, we have our optimized technologies for each expression system: back power for bacteria expression, yeast high for yeast cell expression, BACU1 for baculovirus insect expression, and manpower for mammalian expression. Manpower is a technology licensed from National Research Council of Canada for rapid recombinant protein production in high yield. For big molecular weight protein, we use double tag strategy for pure protein with improved production efficiency. In summary, our service is backed up by our advanced technologies to ensure the high quality of protein. Another big advantage of GenScript protein services is that we are one-stop service from sequence to purified protein. What we need from you, just the protein sequence. We start your project with gene synthesis, in which codon optimization is typically incorporated. We guarantee the amount of the protein and the purity of the protein. Barely company offers such comprehensive guarantees. We have the full spectrum of the expression systems available. No matter which one you choose, our optimized technologies in each expression system ensure the high production efficiency, which means high quality protein at low cost to you. We also offer bioprocess services for mammalian expression. Research labs seldom have the capacity for large-scale protein expression and purification, as large-scale production requires expertise and special equipment as shown here. GenScript offers flexible production scales from meg to gram level production with the fast turnaround time. From sequence to purified protein, you can get it in as little as 4 weeks. No other companies can beat us on such fast turnaround time and comprehensive guarantees. No matter what kind of protein production projects you have, you can find a solution here at GenScript. We offer a variety of protein services covering almost every aspect of recombinant protein expression and purification, from full portfolios of expression systems to stable cell lines, from protein expression evaluation and optimization to large-scale protein production, to protein crystal for structure biology studies. We also equipped with the largest capacity on high-throughput protein variants services. We can produce over 1,000 protein variants in just 30 days. For some really hard-to-express protein in vivo, we offer alternative chemical protein synthesis services. In summary, GenScript is your one-stop shopping place for your protein services. We are flexible and capable enough to accommodate your specific need on your protein production. So far, GenScript has delivered over 5,000 proteins in 4 expression systems. Our statistics showed 95% success rate for all protein projects. The left side chart shows you the number of proteins expressed in bacteria, yeast, insect, and mammalian cells separately. The right side pie shows the percentage of different types of proteins that have been successfully produced at GenScript, including some difficult proteins such as transmembrane proteins, proteases, etc. Besides protein services, we offer a broad range of services to make your research easy. This slide gives you a general overview of the services we offer at GenScript, including gene synthesis and subcloning, peptide synthesis, protein expression and purification, custom antibody production, discovery biology services, and stable cell lines, all with the goal to make your research easy. More than 9,000 peer-reviewed journal articles have cited GenScript services and products, making GenScript the most frequently cited biology CRO in the world. I'm very proud to be part of it. This wraps up my presentation. Here is a list of our coming webinars. Please feel free to register if any of them is interesting to you. Thank you for your time and attention. I see that questions have been coming in all along. The first question, I'm interested in bacteria protein expression. How much do you charge for it? For bacteria expression, I would recommend our back power guaranteed packages. You have the option of producing tagged or tag-free proteins with varying purity options, 75%, 85%, or 90% purity, and with 3 different endotoxin level options. It starts at $2,200. And the best part is that gene synthesis is included in those packages at no additional cost. We guarantee the amount and the purity of your target protein, and there is no cost to you if the project fails. Delivery time is as little as 6 weeks. Second question. I plan to use SOMO tag. Anything should I pay attention to? SOMO tag is a member of the ubiquitin-like protein family that regulates a variety of cellular processes like apoptosis, cell cycle progression, etc. Studies show that fusion target protein to SOMO can lead to increased expression and solubility of your target protein. It seems to work well, and given its relative small size. This tag also serves as a protease tag, and protease treatment results in production of your native target protein with no actual amino acids. However, the efficiency of SOMO protease can be problematic for wider application of the tag. Third question, your protein expression evaluation, how many conditions do you test? A good question. It depends on the packages. The service we offer for protein expression evaluation called Potential that offers 3 tiers of services: standard, silver, and gold packages. For standard packages, we test only 1 condition to evaluate whether the protein expressed in your chosen system with your chosen construct, and whether it's soluble expressed or expressed as inclusion bodies. With the silver package, we test 8 different conditions by optimizing growth temperature, media components, and inducer concentrations. With the gold package, we test 48 different conditions, optimizing not only the 3 parameters I just mentioned in the silver package, but also promoters, host cell strains, and fusion partners. Potential Gold package is the most robust industry-first high-throughput expression and solubility optimization matrix. Another question here is why cell-free system is not good for large-scale protein production? There are a few advantages of using cell-free systems over cell-based systems. For example, you can express toxic protein easily. And you could express multiple proteins using one reaction mixture. However, it would be very expensive for large-scale production. Typically, it's going to cost $30,000 to $40,000 for about 10 mg protein. Another question, you mentioned a price match promotion, how it works. Yes, we just launched a price match promo for our bacteria expression services called Back Power Guaranteed Packages. As we are confident with the quality of our services, And we want to eliminate any concern you had with price. We just need to, you just need to submit a competitor quote to us by email protein@genscript.com. Our technical account manager will provide you a quote matching competitor's price, given that the competitor offers a service at a similar level as us. Due to the time restraint, I take the last question. Several of you asked whether you can get a copy of this presentation. Yes, as I mentioned earlier, this webinar has been recorded, and we will post both the slides and recording on our website. You can visit www.genscript.com/webinars to download them. You can also find other archived and upcoming webinars there to see whether any of them is interesting to you. I'll stop here. And right after this webinar, there will be a quick poll on your screen. Please take a moment to complete. We love to hear your feedback. Again, thank you all for your time and attention. And on behalf of GenScript, I wish you all success in your research.